Alright, now scalar vectors. Here's the deal with these. Basically what you're going to be doing with vectors that have a scalar quantity attached to them, such as this one where we're going to take vector A here and now sketch a vector called 3 times A, is you're basically going to take this length here for vector A and make it 3 times as long. So you can see here what they've done is they've taken that vector A, they've created 2 extra vector A's and put them tip to tail there and created a vector that's, as we said here, 3 times as long. You won't typically make a vector. I don't need to see those arrows on there, so if they're asking you to deal with 3A, just treat it just like this as one whole vector quantity right there, and so that would be 3A. So let's take a look at these examples and how we can apply vector quantities and also at the same time do sums and differences with vectors. So in this example here, notice what they're asking us to do. They want us to take half of vector v and add it to vector w. Now what you're going to see me do here in these next 2 examples is I'm going to use tip to tail method here. I prefer to use that in most cases when it comes to vector quantities. So half of vector v, here's how you wrap your head around that one. Vector v goes from start to finish here and it's this long. So when they say half of v, just make it half as long. So just estimate it as best you can. Make sure you keep the direction in the same manner here, and so there we go. There's half of vector v. Let's write this one in here. So there's half of vector v. And now what they also want us to do is combine this with vector w. Now vector w, right down here, is this quantity. Now we don't modify this one at all, it still stays the same length. So when we have vector w now working for us here, realize now if we really want to do tip to tail here, let's go ahead and take this vector w here, and let's just move vector v just like this. So now I'm doing tip to tail here. So let me erase this here and move half quantity down here. So there's half of vector v. Here is vector w. And if I'm doing tip to tail, we can see now where the new resultant vector would go is from start to finish. Remember, it's not going up here and then also at the same time going in this direction here. So there is our tip to tail. And so this is our answer. Don't forget to write in what quantity that you have there for your resultant vector. So half of vector v plus vector w. Let's take a look at the next example. Still using the same 2 vectors, vector v and vector w. Now they want us to take vector v and subtract half of vector w. So let's grab vector v in its full glory here, which is what we have right up there. So let's just take that one and copy it and put it down by vector v. So now what we also have to do is now take a look at vector w, but we need to cut vector w in half. But another thing to notice here about this one, this time, is now we need to subtract half of vector w. So how do we do that? Let's take a look back at vector w. So the trick to getting this vector correct is you got to look at two different motions here. First thing is we got to take a good look at vector w. Notice it's going up and to the right in this direction here. However, also note that it's half of vector w. So if we need to have half of vector w, we need to trim this vector down a little bit, don't we? So we need to cut that in half. So let's go ahead and do that. So there's about vector w there. Not only that, when there's a subtraction sign going here, what we're going to do with this vector is we're going to switch it around to make it go in the other direction. So there's about half of vector w. So now we're going to take this half of vector w, and now we're going to do tip to tail with the vector v that we had down below. So now we'll connect these two using tip to tail. And now if we have vector v, which was right in there, let me grab that back out of here, put it over here so that way we can see it. Oops, I moved that vector, which I don't want to do that. There we go. And so now this is minus half of vector w, then that means our resultant vector, if we're still doing tip to tail, started here, we go up and then down this way to that mark right there. So there is our resultant vector of vector v minus half of vector w. Now, one important concept of vectors that's important to master going forward in later sections is this whole concept of getting component vectors of a given vector. So consider, for example, here vector x here, which goes up into the left here. Every vector can be broken down into components, and the most useful components that we can create with a vector is a horizontal component and a vertical component, which you can see here. Vector x can be made of two components here. We can see that vector p, indicated right here, oops, vector p right there, that is the vertical component, and then we can grab the horizontal component, which you can see right here, which is vector q. So those two vectors are what make up the vector x. Notice that if we were to take a good look at vector p and vector q and do a tip-to-tail method, we create vector x right here. If we started here for vector q, then went here with vector p, vector x is right there going from tip to tail. So where that comes in handy is when we look at particular vectors, like this situation right down here, with this boat going in this direction here at 15-mile-an-hour clip, we can figure out what those horizontal and vertical components are. So let's go ahead and calculate those. Let's zoom out a little bit here. So for this particular example, what we're trying to do is find the vertical and horizontal components of this. We do know that the boat was traveling at 15 miles an hour. Its direction, its bearing was 65 degrees north of east. So if we're trying to calculate this here, there's a real big point to all this, is that we just made a right triangle. So we can use SOHCAHTOA here to find these components. So if we're trying to figure out this side here, which maybe we can just call it y, then the relationship between the 65, the y, and the 15, you got it, it's sine. So the sine of 65 degrees would be equal to opposite of hypotenuse, so y over 15. So now to solve for y, you guessed it, we have to multiply both sides by 15. And when we multiply both sides by 15 to get y by itself, that means that our answer here for y is going to be about 13.6. So we're writing here 13.6 miles per hour. That's the vertical component. Now to find the horizontal component, let's just write that with an x. To find that one here, you guessed it's cosine. Notice the cosine of 65 degrees, the same angle there, is going to be equal to adjacent over hypotenuse, so x over 15. So notice in this case we got to multiply both sides by 15. And so when we do that, we get an answer here of 6.3 miles per hour. Okay, so this concept of getting these components here, it's really not a tricky concept because we've done all of it before with SOHCAHTOA. So some final thoughts here. Vectors do have a lot of practical applications. A brother of mine is a pilot, and so one thing that he deals with on a regular basis is vectors. Suppose you're flying from Detroit to Chicago, and that plane is flying at a speed of 188 miles per hour. But suppose there's, coming off the Lake Michigan there, you got yourself a 20-mile-an-hour wind. Well, with that 20-mile-an-hour wind going in that direction, blowing it southeast, it's going to affect that plane's trajectory. And the way that plane's trajectory gets affected is just using just basic vector quantities like we had here. I kind of joked with my brother in saying that, boy, the situation I'm giving the kids today is pretty simplistic and pretty trivial to a pilot. And he said, actually, it's not that far off from what we do. He just says, we just have an app to do this kind of work. We have an app that does this kind of work right here. Or he has a tool that does calculate that. The thing is that he has to worry about is just doing it on the fly all the time, because weather, you can't really trust a weather report, and don't we all know that? So that's 8.1. We'll have 8.2 in just a little bit.